So let's take a look at a vibration application. So this is some research project that I've done with vibrating plates relating to detection of IEDs and landmines using vibrations. So in order to create this vibrating plate for this research project we were working on here, one method in which we looked at doing this was utilizing rotating magnet vibration testing setup here. So for the first initial prototyping of this, we just wanted to see if this concept would work. So what we did is we took a magnet with a north-south oriented along this axis here and rotated it in a drill press. Now the drill press we could set the RPMs at pretty easily with the pulley system up top and the belts. What we wanted to do is we wanted to rotate this at 10 hertz, so 10 rotations per second. So as it spun one time around, it would change from north to south. So you see the polarity change on that there. And we were able to use this ring probe right here connected to a spectrum analyzer in order to measure that frequency. So we could set it with what it says for the RPMs, do our calculations for the right frequency at 10 hertz, and then measure to make sure that that was accurate using our spectrum analyzer. So in this case here, for this system, our spectrum analyzer would be our feedback to let us to know how to adjust this drill press or the rotation of our magnet here in order to achieve that 10 hertz that we wanted to do. Now, as this magnet rotated around, we also had magnets out here and here, set distances away, connected to some spring steel, which was just a hacksaw blade at this point, clamped together, and again, at set distances away from our rotating magnet. So as the polarity of the rotating magnet changed, it would be opposite to what we had here for these magnets. So these are north-south on either face of the magnets here. So as the opposite was there, it would push and pull the magnets back and forth based upon as this rotated here, and then we could see these moving or vibrating back and forth. And the idea would be then we could measure the vibration of these guys here. Now we set the free length of this metal bar so that the resonant frequency matched the frequency 10 hertz of our rotating magnet. So we could do some calculations based off material properties and distances here in order to figure out how we could set that length correctly to hit that resonant frequency. So this is what we were seeing on the spectrum analyzer, so that ring probe that I showed on the first slide there, our spectrum analyzer for 3 different cases here, with no vibrating magnets attached, with 1 vibrating magnet on that spring steel, and then with the 2 that we saw in the picture there, vibrating magnets there. This is the feedback we were seeing, the results that we were picking up with our spectrum analyzer. So without any vibrating magnets there, what we'd see is right at 10 hertz, this is 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50 right here. So these are 5 hertz increments in between each of these gradients there. So this is right at 10 hertz, exactly what we wanted to see. So we had our drill press adjusted correctly using the feedback information that we obtained from the spectrum analyzer and that probe. And we could clearly see right here we have that 10 hertz spike right there, and then kind of just background noise of the room across the rest of it there at the other frequencies. Now, when we put 1 magnet here at the right distance there to get the resonance there, what we started to see was not only we were seeing that first spike right there just from the rotating magnet, but then we were also seeing the spike here at 20 hertz, or 2 times our fundamental frequency right there, and a little bit out here at 3 times our fundamental frequency right there. And then when we put the 2 vibrating magnets in at the correct lengths to hit resonance there, again, we saw that same initial one with the same amplitude right there. We can see the same amplitude across that right there. And what we saw now was for this guy here, we now saw a little bit stronger spike at 2 times the fundamental frequency, or 20 hertz, and a little bit stronger spike there at 3 times our fundamental frequency, or 30 hertz. So the next step in this design process was to create a faster spinning rotating magnet in order to achieve some higher vibrations of a plate here. So this is what we came up with. We can see we have this servo motor over here, just a DC servo motor that we can change the speed by just changing and varying the voltage that's going to it. And this is connected to just a little chuck here that's spinning and our vibrating magnet right here at the end. And then we can see we hard fixed our other magnet right here, the same ones that were on the spring steel in the first prototype. Proof of concept, and this is on a stage here that translates only purely up and down right here with very smooth bearings, so that could move freely there. When up top here, what you can't see is there's a flat plate there. That'll be our actual vibrating plate. So we get this thing started spinning, comes up top, and now you can see right on this plate right here, coming close, it's vibrating right there. So the concept worked, and we were able to create a little test rig in order to use a rotating magnet to create a vibrating plate. Now, the next step of this is how do we control this? Where's the feedback loop in this? How do we know this is exactly spinning at the right frequency? Well, we can use that probe again. How do we know what frequency the plate is actually vibrating at relative to our initial given frequency here? So all of that information we can use with sensors. So that's where we put the sensors in as part of our feedback loop. So some of the sensors that we could use within this is we could use an accelerometer to measure the vibration. We can use an optical laser displacement sensor to measure the displacement there. And ultimately what we want to do when we're talking about detecting landmines is we're going to want to use radar, or ground penetrating radar, which is GPR, where we have a known signal coming in, reflecting off that flat vibrating plate and coming through up through a receive antenna with a reflected signal. So that was the next step that we did there. We took this servo rotating magnet and vibrating plate setup that we built here, and we set this on top of a sandbox and turned it on so that we had the metal plate vibrating just as we showed in that previous video there. And then we used our GPR system. So we have a GIMA antenna, which stands for Good Impedance Matching Antenna, that we had developed and built, and this was used to send out a known source sine wave. So we had a 4 gigahertz sine wave coming from a signal generator, a very high-end one that we could control very, very accurately and had its own internal feedback loop, so we knew we were getting a pure 4 gigahertz sine wave out of it. And then we had a second receive antenna over on the right next to it there, which was used to receive the signal into a spectrum analyzer as it reflected off this top vibrating plate. So one of the important things with any of these practical tests is to figure out what your background noise in the room is, or your testing area, or as we saw previously in the other chapters, what is our disturbance? What is going to be causing errors here just from our natural environment? So the first thing we wanted to do was turn this on without any vibration. So within that test rig that we had built, we put a lock in it. So when we put this into its lock position, we still have the noise of the motor from the electricity, the DC current going through it. We still have the rotating magnet, but the stage was locked in spot, so we could not get the plate to move. It was staying perfectly flat and not vibrating at all. So we wanted to do that and acquire our signal through the GPR system here with that sent out 4 gigahertz sine wave there, and see what we see with background results with no shaking. So that's what we see down here below in this graph right here. So we have this servomagnetic rotating magnet with a metal plate in lock position, so it's not moving here. We can see our fundamental frequency right here at 4 gigahertz right there, and we are seeing these small spikes over here right there. So we do see our transmit signal being reflected up, and we do see some small variations likely due to the rotating magnet, because we can see where these are based upon that, and we can double check, is that the actual frequency of the rotating magnet? So there's where our feedback loop comes in. We can put that probe on the magnet, hook it up to the spectrum analyzer, figure out, okay, that's from the rotating magnet. These are the spikes we're seeing, and this is not from the small vibrations that we're hoping to see eventually once we unlock that top vibrating plate. So now that we had that background information and could see when we have that plate locked and there's no vibration, what our signal looked like, our background signal, what we do then is we unlock the plate from its initial position there and allow it to vibrate. So then we compare the no vibration when it's locked to the vibrating plate right there with our reflection off the surface using our GPR and our GIMA antennas. And what we see here is, yeah, here's our background, our fundamental frequency, our 4 gigahertz coming in. We have these 2 spikes right here, likely due to the rotating magnet itself. But now we're seeing these strong spikes right here from the vibrating plate. So this was very, very promising results for us here. And what this showed is we could have a vibrating plate buried under the ground that we can't see, we can't hook up with an accelerometer, we can't use an optical laser displacement sensor, but we can show that there is something there that is vibrating, and from the information, the amplitude here, and our frequency values, we can back out the depth where that is as well. So this is going to be very important. And the idea behind this concept is if you have some of these new IEDs and landmines in an abandoned minefield where they've come up with some very creative shapes and materials that can't necessarily be detected on their own with a metal detector or traditional GPR, where it's not vibrating because it's made of organic materials and it has some surfaces on it that look very natural and are not smooth, flat surfaces that we'd like to see for a GPR data and a reflection. So with all those tricks thrown in there, as they develop these IEDs and landmines, we need to figure out a new way. So the idea being, could we shake the ground somehow? use acoustics? Could we use some type of device in order to shake the ground and have the soil vibrate at one frequency, but then this landmine or this IED vibrate at another frequency, and then be able to pick that information up with radar? So we could completely do this non-contact. So we could have something fly over top, a drone or a boom over the top, putting out an acoustic wave into the ground, vibrating the ground with that, which causes the landmine that's buried in the ground to vibrate just slightly, and then we come over top with some GPR antennas and equipment with a known frequency as our source, and we can look at our received signal and say, hey, there's something there. So that's the idea behind this project and how we can utilize vibrations in order to detect underground landmines and IEDs. So the next step was to actually bury this guy here, tweak a couple things with it, really pay attention to that feedback control mechanism, all the information that we've gathered so far from our spectrum analyzer, and we put this in a box here and buried it. And here's our two GEMA antennas, our transmit and our receive antenna right here, and can't see anything. Underneath this is all completely buried in the ground. So then we repeated that same experiment again with this buried right there with the test place setup. So we do that, and even buried, we were able to see it through the sand right there. See those two spikes? So buried with no vibration, buried with vibration. So buried versus unburied wasn't a huge difference there, and this was very, very promising again, because now we realize this is a more practical application here. It's not just a pure metal plate vibrating in the air. We've actually buried this in the ground and utilized our GPR antennas with that known sine wave coming in, and we're able to see clearly when something was vibrating underground. So with the design process, there's always revisions, modifications, and adjustments. And one thing we noticed with the first servo motor was it was rather finicky, and it was just DC power controlled. So having it set to a known RPM and a higher known RPM was not great, and it varied a lot. If there was any extra loads on the motor, it wasn't locked in spot perfectly. That initial frequency, the rotating frequency of our magnet there, tended to be not so stable. So we could get that feedback information again from our probe, and now we could even get it from our GPR antennas or accelerometers as well. So what we did was we bumped up to a higher quality motor here, servo motor here, with a whole motor controller system, which again has its own feedback control system. So we've talked about this in previous chapters, previous lectures. So that in itself is a whole nother control system right here that we utilize in order to get this just right and have a very clean rotation frequency of our rotating magnet there. Bolted things down, used some Loctite within this so that we're only purely going up and down with our plate right there with this new servo motor. Tested this out again, did some higher frequency surface tests above the ground. And you can see here's an above ground test is sitting in our sandbox right there. And you can see our send and receive, our transmit and receive ground penetrating radar antennas there, our GEMA antennas right there, and repeated the same test as before. Now, another thing that we did along the way was we also did multiple sensors. So we didn't want to rely on just, okay, the feedback control or our information we retained from our motor, but we also wanted to place an accelerometer on this and a laser displacement sensor on this as well, so that we could get the exact frequencies from the accelerometer and its displacements and frequencies from our laser displacement sensor. So here we have an actual video of this upgraded with the new servo motor, the whole vibrating plate system sitting in our sandbox, not buried at this point yet, with our whole motor controller system that we have set up over here going to this, so we get feedback directly from our servo motor down here, so we know the exact speeds all through our feedback control system within our motor controller here. And we ran this. So we can see, zoom in here a little bit, come down in, you can see that magnet rotating down there. You can hear this a little bit as well. You can see that thing, that is going at a really high frequency as compared to the last time we saw it. You can see it just looks blurry almost in the video at the high frequency we have there. And up above we have our transmit and our receive GEMA antennas directly above that flat plate with that set 4 gigahertz sine wave coming in, and looking to see if we can detect in air, just sitting on the sandbox here, the vibrations of this plate here. And again, compare that vibration, that frequency, to the information we can obtain from an accelerometer sitting on here and a laser displacement sensor on here as well. So here is our spectrum analyzer data from the rotating magnet vibration plate setup at 105 hertz now. So we've gone up quite a bit now. We're rotating that magnet at 105 hertz rather than when we first started in our drill press, we only had it at 10 hertz there as a proof of concept. So now we're really cranking through this at a nice high frequency right there with a good system setup, a good motor controller. And we can see there's our fundamental 4 gigahertz right there from our transmitted ground penetrating radar antenna right there. And now we're seeing our vibration right here at that 105 hertz. So right there, there's 100 hertz, there's negative 100 hertz, just off that line there, right at that 105 hertz. So this is very, very promising that we can easily detect an exact vibration using ground penetrating radar in a fundamental frequency. And we can see the carrier frequencies over here at that 105 hertz, which is what we're rotating the magnets in order to achieve that 105 hertz of that vibrating plate. And again, we can verify that vibrating plate that it is at 105 hertz by putting an accelerometer on it and a laser displacement sensor.